Hi, I'm Daniel Crapo, and this is my Diagnostic smoke machine. The fundamental problem that this project solves is that leaks in any sealed system, whether it's a specialized laboratory vacuum, an HVAC duct, or a water bottle, are often microscopic and completely invisible to the human eye. Finding these leaks takes a lot of guesswork and wasted resources. My solution generates a pressurized, visible smoke stream that helps to pinpoint these leaks instantly. In this video, I will first demonstrate the hardware, internals, and my custom 3D printed enclosure. To provide clear visible evidence of my PI and proportional feedback loops, I will perform a demonstration using a water bottle to show the pressure sensors and pump, as well as the thermistor and heating coil, reacting to real-time changes. I will then show a practical application on an engine. We have 3 user inputs. We have an on-off button. We have an encoder to adjust the target temperature and the time. And then we have a potentiometer to adjust the pressure. On the rear, this 20x4 LCD acts as my display. It provides a live dashboard showing the actual versus the target values for both pressure and temperature. It also displays the timer and the on-off status of the pump and the heater. To demonstrate the PI and proportional feedback loops, I've set up this side-by-side view. My code uses a proportional integral controller to manage the pump based on the error between my target and the pressure sensor. I will start the test by selecting my temperature, which will keep at 175. We then confirm by pushing the encoder. We can adjust the time with the encoder, and then we set it with the encoder again. We'll turn the potentiometer down for just a second. We can start the target at 0.5 psi. You can see the bottle start to expand on the right. As we watch the LCD on the left, we can see that the pump P1, which indicates on, will flicker on and off as the pressure drops below the target. If I manually squeeze the bottle, we can see that the sensor detects the pressure increase and the loop keeps the pump off. As soon as I release it, the loop instantly kicks the pump back to P1 to recover that pressure. At the same time, the 10K thermistor monitors the heating chamber. For this demo, I've capped the target at 175 degrees. This provides a safe vaporization point, while the proportional loop prevents the heater from overshooting and damaging any components. All right, let's show you how it works on a real engine. I've got the machine hooked directly into the intake manifold. An engine's valve sequence usually leaves at least one valve open to the atmosphere, which means we can't get a perfect seal and the pressure will not build. I'll flip the system on, and if I remove this vacuum hose, you can see that smoke coming out immediately. It definitely shows up better with a light near it. On the rear, we have a removable panel. Now that our battery and heating chamber is removed, we can see the inside a lot better. Up here, we have the HX710B pressure sensor. Here in the jar, I have my 10K ohm thermistor that's inserted down with the hose. This is the heating chamber. We used a mason jar to be able to hold the oil while also withstanding the temperatures. There's a fiberglass wick that picks up the mineral oil and brings it to the heating coil. The heating coil is made of nichrome wire. This is my primary actuator, the 12-volt air pump. It is driven by the PI feedback loop to maintain a consistent PSI. Here are my MOSFETs that control the pump and the heating coil, my buck converter, and my nano. I have gained a lot of new skills during my research, design, construction, and coding of this project. I have lots of changes I would like to implement to make it even better in the future. Thanks for watching.